Hi guys, Rukved Nakare here from torsionaltraining.com. Thanks for joining us. I hope you've been enjoying the course so far. I have a really cool lesson today. It's the second lesson from module number 2. I'm going to be teaching a very important concept in torsional vibration, and that's the interference diagram. And I'll be using an engine model to illustrate the importance of a interference diagram. So this time around we will fire up diarobes right away, and we'll model up the engine model, and then we'll crank out the interference diagram from the engine model, and then we'll come back to this presentation and I'll discuss the concepts in this presentation. So fire up diarobes, see you there. Okay, so I have diarobes fired up, and I have a great example for you guys today. This is a mass elastic table of an engine model, and it's driving a propeller. So I believe this is a marine installation, so one of those maritime ships. And it's really cool because it's a 4-cylinder engine and it's driving a propeller. And I have the inertia values here, and they are a little adjusted based on some numbers that I was trying to match on towards the natural frequencies. But these are pretty realistic values, and these stiffnesses here are also pretty realistic values for this kind of machine. So I think you're going to enjoy this because I'm going to use this particular example in this lesson and possibly the next lesson, where I'll be explaining a lot of concepts with respect to interference diagrams for motor drive units as well as engine drive units. So let's get started. So let's begin by modeling this mass elastic table. Go ahead and click on data editor, and we will repeat the steps that we have been using the last couple of lessons. So consistent English units, call this mass elastic table call this engine 4-cylinder driving a propeller, and under material, again, since we're doing an inertia stiffness model, go ahead and click on material 0 0 0. I'm pretty sure everybody's familiar with these steps now, and I like to call this dummy material. So I'll be moving a little fast in building this model so I can get to the main point rather quickly. So element number 1, sub 1, material 1, 0, give it a random length of 10, mass ID 0, mass OD 0.001, 0, 0.001, and cylinder 1 dash cylinder 2. So remember, we're creating elements right now, so the elements are always formed between two stations, and the inertias are placed at two stations, and there's a stiffness spring in between the two inertias. So the element, I call it, since the inertias are cylinder 1, 2, 3, and 4, element 1 is between cylinder 1 and cylinder 2, so cylinder 1, cylinder 2. Element number 2, 1, 1, 0, 10, 0, 0.001, 0, 0.001, cylinder 2 to cylinder 3. And so your final table should look like this. So we have 4 elements, we have a total of 5 stations, and the elements are modeled in here, and the last element's between the 4th cylinder and the propeller shaft. So after developing this, go ahead and click on disks, and let's go ahead and put in our inertias. So let me minimize this here. So now let's model the stations. So again, it's a rigid disk, station number 1. It's got a polar inertia of 1.112, and call this J1, or you can call it cylinder 1, your preference of course. Rigid 2, 1.112, and J2, or cylinder 2. And your final table should look like this. So we have 5 inertias, each inertia for each corresponding cylinder, and then the fifth inertia is for the propeller. So that is our inertia table. So go ahead and close this, and it populates the table. And then now we're going to put in our torsional stiffnesses right here. So go ahead and click on torsional slash actual, and again linear model, so click on linear connectivity and T for torsional. We want K1, which is connecting station 1 and station 2. So since it's a flexible spring, click on flexible, and 3.40 e to the 6th K1. Right, so I'm referencing these values right here, and they're all the same values. So your final table should look like this. So there you go. We have our inertia table modeled in, we've got our shaft elements modeled in, and now we have our torsional connectivity, our stiffnesses modeled in. So our inertia stiffness model is complete. So click OK, hit save, give it a name, example 2. So save and close. Yes, and there you go. There's our model. So after doing this, remember this is a demo version, and so my main task here was to keep the number of stations under 5 or 5, so that we could run this model and see what the torsion natural frequencies are. So you should be able to run this model with your demo version. So go ahead and click on analysis and click on torsional vibration. Now before we move ahead and solve for the natural frequencies and modes, I'd like for us to step through this model summary real quick. I always like to check this before I run a model, and I know in the last lesson I didn't emphasize this as much, so I'd like to go ahead and emphasize this again. So click on run, and it obviously brings up that, and hit close. Then go to model up here and click on model summary, and it should open up this notepad file, this text file. So scroll down. Let's just make sure what we've modeled in is what Diarobes is picking up. So we have 4 elements, which is correct. We have 1 material, which is correct. We have 5 inertias or 5 disks, which is correct. We have 4 springs, which is correct. And all these values are correct. We've got 10 inches in between. And we have our polar inertias modeled in at every station, which is correct. And this is our total inertia in the model, and this is our, here you go. I'm so glad I did this. I caught an error. We got 3 of the springs, and the 4th spring, I entered the value incorrect. So this helps a lot in cross-checking your model, and I'm really glad I did this. This is a perfect example of where you can go wrong, especially when you have very long crank trains, and if you input a wrong stiffness, it'll change your values off by so much, and you'll be scratching your head thinking, well, what's wrong with the model? So this is a perfect example. So I'm going to close this and fix this spring between station number 4 and station number 5. So closing this, going back into model, clicking data editor, clicking torsional under slash actual, linear connectivity, and there you go. It's 3.46 e to the 6th, and that should fix it. Click OK, hit save. Alright, and now our model is complete. Now we'll go ahead and solve for the natural frequencies. So as always, click on analysis, click torsional vibration, change this to natural frequencies and modes, and hit run. Of course it brings that up, hit OK, and it solved it. Go to post processor, under natural frequencies and modes, click on mode shapes, and there you go. These are your mode shapes. Click on the 2D view. I think it's very interesting, the 2D view. There you go. You got most of the movement in cylinder number 1, and go ahead and turn on the station numbers so it's a little easier to follow. Click OK. So there's your station numbers. Cylinder number 1's got the most vibration, and the propeller shaft is quiet in this particular case. So going on to the next mode, there you go. Again, cylinder number 1 is vibrating a lot, but number 2 is quiet. 3 and 4 are vibrating, and then again the propeller shaft is quiet. So in this particular mode, you would be concerned about this area quite a bit. Let's go ahead and animate this. Yep, there you go. And you can switch back to the first mode. There you go. And then of course, if you want to see it in 3D, that's what it looks like. So you can see in the 3D view a lot of vibration up front here. So if you happen to have some sort of equipment mounted to the end of this shaft, which is geared supposed to this shaft, then you may have a lot of vibration being caused on some auxiliary equipment as well. But this is a classic mode that you see in some of these machines where the engine is vibrating together, and then there's a little bit of an inflection point where the last cylinder is connected to whatever piece of shaft or machinery that it's driving. A lot of the vibrations and flexibility are in this particular, are on the engine side. So again, if you were to be concerned about where you'd have a failure, these are all moving together, but you can see this is the inflection point right here. So you would look at this area closely to see if there's some sort of problem, uh, failure, or a potential failure taking place here. So one of the main concepts of this course is the interference diagram. If you can understand an interference diagram, then you can understand the machine instantly. And what I mean by that is that an interference diagram is a great snapshot of what the machine's torsional characteristics are. So if you can read an interference diagram correctly, then you can tell right away what a potential torsional problem may exist in the machine. So let me show you how to calculate the interference diagram using diarrobes. But before we do that, let's note down the first 2 or 3 modes of this particular model. So I'm just going to note them down here. We have 6037 cycles per minute, which is in hertz. It's equal to 100.61. And then the second mode is, okay, 16,807 CPM, which is equivalent to 280.12. By the way, if you want to convert cycles per minute or RPM into hertz, all you need to do is divide the cycles per minute by 60, because you have 60 seconds in 1 minute. So just to prove that to you, you can take 6037, you can divide it by 60, and there's your 100 hertz, and you can take this guy, divide it by 60, and there's your 280 hertz. So let's get the third mode as well. So it's 25,646, right, which is 427.44 hertz. Right. Now, why has diarrobes plotted these values in cycles per minute or in hertz? So, a lot of rotating machinery can operate at some very high speeds, in which case the general terminology within the rotating machinery world is to use the cycles per minute or the RPM when they talk about the natural frequencies. Now, in the field that I work in, which is more on the reciprocating machinery side, typically, we don't see such high frequencies. We don't deal with such high speeds. Our speeds are more in the, 6,000 CPMs, or really, actually not even that high. More like 1200 RPM and stuff. So we deal in the 20 hertz through maybe 100 hertz range. So in this case, hertz is sort of a more preferred unit for folks in the reset, but in the rotating machinery world, they tend to prefer 6037. But really the same thing. If you divide these values by 60, you can calculate these values. So moving on, I'll show you how to pull out the interference diagram in diarrobes. So go ahead and close this and click on Post Processor and scroll down to Natural Frequencies and Modes again. And this time, we'll open up the interference diagram. So go ahead and open this, and that is your interference diagram. Now, let me zoom this up a little bit, and you can see the interference diagram has some very important information, and I'll get into this in more detail in the presentation. But what I want to point out is you have the natural frequencies on the y-axis and you've got the speed of the machine on the x-axis. But again, just to show you how we got this, I'm going to close this again, click on post processor, natural frequencies, and interference diagram, right? So before we move on to the presentation, there's a couple of things I'd like for us to do as far as settings in this interference diagram go, which will help me explain some very key points in the presentation. So first thing I'd like for you to notice is that on this y-axis we have the torsional natural frequencies, and note there's a flat line for 6037, which corresponds to this right there, and then there's 16,807, which corresponds to this guy, 25646, and so these are the first four torsional natural frequencies of this particular model, and they are plotted as horizontal lines on the frequency interference diagram. So that's the first key point of an interference diagram. So again, it's your torsional natural frequencies that are calculated from the model are plotted as horizontal lines on the y-axis. So now what I'd like to do is I'd like to add more of these lines, and these lines are called the orders of run speed. So the 1x, 2x, and I'll explain this concept in more detail in the presentation, but before we move ahead, I'd like to show you how to add more of these orders on this plot. And the reason why is because it's a very important concept in torsional analysis, and it's part of the presentation, and it'll help me make my points in the presentation a lot clearer. So click on options, go to settings, and where it says excitation slopes right here, type in 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So Dirobes has a limitation of about 10 that it can plot at a time, so it looks like it went up to 10. Not a big deal. So you can see that it plots these 10 run speed orders is what they're called. And now I'll switch over to the presentation and I'll explain what run speed orders are. So welcome to the presentation. So the first question is, what are multiple orders of run speed and why are they important? The best way I can explain this is if you were to take readings on a shaft, either through a proximity probe or through a strain gauge, what you'll find is the pattern of vibration has sort of a complex looking sinusoidal waveform. And if you were to perform what's known as a Fourier analysis, you will find that this signal is really a sum of individual signals or a sum of individual vibrations. So for example, if this were crank angle, which basically means 0 to 360 degrees rotation for one revolution, and suppose you on the left hand side you have the actual vibration, what you will find is that this signal consists of many signals that have different frequencies and that have different amplitudes. So for example, this right here, the blue line, which is called 1x, right? It is a signal, or it's a vibration that occurs within the full revolution of the shaft. So it is one cycle, which is a classic vibration waveform, through the complete single revolution of the shaft. Similarly, this guy right here, which is the 2x, right? It has this vibration pattern repeats itself twice in one revolution of the crankshaft. Similarly, in this case, this pattern here, which is sort of red in color, it repeats once, twice, and thrice in 3 revolutions. And this last one here, just for exaggeration, this particular pattern repeats itself 8 times. So this vibration cycle repeats itself 8 times within one revolution. So that's the meaning of the 1x, 2x, 3x. It basically means if your 1x is your fundamental frequency of the machine, which basically means, for example, if you are running at 1200 RPM, then your fundamental frequency is 20 Hertz, Your second x frequency will be then 20 times 2, 40, and the third x will be 20 times 3, 60 hertz, and the fourth x or the 8x will be 20 times 8, 160 hertz. And so let's take this a step further. Now, going back to the classic vibration equation, right? You have the J theta double dot plus damping into theta dot plus the stiffness into theta is equal to torque. This is the classic vibration equation in the torsional sense. Now, what we're looking at really is the right-hand side of this equation. The left-hand side is the response, the right-hand side is the input. So the left-hand side is, mass times acceleration, and the right-hand side is force. So similarly, in this case, this is your torsional excitation or your response due to your input, right? And what happens in machinery is that this input signal is not a simple sinusoidal signal. It's actually a combination of several sinusoidal signals shown here, which are at multiple orders of the fundamental run speed. So what I mean by that is if this machine has the fundamental frequency, for example, which is 20 hertz, then its applied torque, there will be an applied torque at 20 hertz with a certain magnitude. There will be an applied torque at twice its frequency at a certain magnitude, and then so on and so forth. There will be an applied torque even at 8 times. And specifically in engines, it's even more intense. It's up to about 24 orders of run speed. So going back to the previous slide, why is this important? So this is important because really the input that we're applying to the crankshaft has multiple orders of run speed, right? And because it has multiple orders of run speed, the crank experiences torques at all these frequencies, right? And because the crank experiences torques at all these frequencies, the crankshaft material is experiencing this torque, and stresses are generated at these different frequencies, and these can cause failure. So we have to account for all the different types of torques that are applied to the crankshaft material, right? And so if we want to do a torsion analysis, we want to make sure that we're accounting for all the different torsional excitations that will take place in the machine due to the driver. If the driver is a motor or if the driver is an engine, it doesn't matter. We want to account for all the possible torsional excitation, or basically all the possible input torques at all the possible frequencies that are of concern. So why we study multiple orders of run speed is to account for all input torques at the different frequencies. So I've been referring to this concept of fundamental frequency and multiple orders, and I want to show you how you calculate these fundamental frequencies and multiple orders of the fundamental frequencies. So going on to the next slide, assume you have a machine that is running at 1200 RPM, then its fundamental frequency is 20 hertz. And how you calculate that is you take the machine speed and you divide it by 60. So you get 20 hertz. And why you do that? Simple concept. So if you want to go from your RPM to your frequency, then you just divide it by 60. So your 2 times will then just be 2 times 20, which will be 40 hertz. Your 3 times will then be 3 times 20, 60 hertz, and so on and so forth. And your 8 times will be 80 hertz, 160 hertz. So another very important concept that you see in a lot of vibration textbooks and a lot of vibration readings is the concept of the fast Fourier transform. And what it is it's a mathematical construct to convert your time domain data or your angular domain data into frequency domain data. And it's really great because this is how you can tell what number of orders, or rather what orders in your machine are of great importance. Like for example, in this case, if I were to take the FFT of this signal, the fast Fourier transform of this signal, I can see right away that I have an excitation at 1x, 2x, 3x, and then I have no excitation between 4, 5, 6, and 7, and then I have an excitation at 8x. And the other nice thing about the FFT is that it tells you the amplitude. So I have something really cool to show you guys on the next slide. Check this out. This is a great slide. I have done a lot of these calculations, and this is the torques experienced by the engine crankshaft due to the combustion process. So when your firing impulse goes off on the engine, this is the torsional excitation of on the crank pin of the engine, and it's 24 orders. As 24 orders. These are 24 orders. This is the fundamental frequency, and all these other frequencies that you hear are between 1 and 24 times the fundamental frequency. And it's basically torsionally, it's very violent, right? And so the combined signal looks like this, right? Which is kind of a very nice, pleasant looking signal. But if you were to take the FFT of this signal, or if you were to perform a Fourier analysis of this signal, this is what it actually looks like. So if you don't account for all of these excitations in the crankshaft, then you may miss a particular high energy excitation. And what I mean by that is, suppose I only took some of these signals, right? And I didn't take all 24. And suppose when I was being selective about my signals, I didn't take this particular signal here, right? So which looks like it's the 2 times signal, and it's almost about 60, right? Its magnitude. So had I ignored this signal in my analysis, then suddenly a pretty significant energy that is being applied on this crankshaft in reality is now not being applied in my analysis. And so if I'm not applying it in my analysis, then the predicted stresses in my shaft will be wrong because there's a significant energy that's been ignored. So it's very important to consider all the important orders of run speed in a machine. And so that's why we have the interference diagram, which forces us to recognize that there are multiple orders of machines which have a excitation, and so we cannot ignore any of these applied torques in the crankshaft. So now that we understand what the multiple orders of run speed are, let's now go back to the interference diagram, and now let's break down the interference diagram so we can understand it a little better as to what is really happening. So this is the interference diagram of the model that we built earlier, and you can see that what's plotted here on the flat lines are these torsional natural frequencies, these horizontal lines, and what we have is from 0 to 5,000. So assuming that this machine is going to run for this speed range, so from 0 to 5,000, then its 1x is going to look like that, its 2x would look like that, 3x, 4x, and so on, up to 10x, for example. And you know what? Let's not take this at face value. Let's prove that this is correct. So let's close this for a second, minimize this, and I'll pull up Excel, and I'll show you how to build an interference diagram. It's very easy, and I always like to do such things and challenge codes and challenge assumptions. It's really easy to just accept that an interference diagram looks like this, but I really want to prove to you that an interference diagram is a great concept, and it's a really easy concept, and you can construct an interference diagram without needing diarobes or any other software for that matter. So let me show you how we build an interference diagram, and I think it'll drive the concept of the multiple orders home very quickly. So let's assume that the machine speed is 1200 RPM, right? 1200 RPM, okay. And so now on the x-axis you have rotational speed, right? And on the y-axis you have also speed, but you're plotting the torsional natural frequencies, but really it's speed. But I'll show you how we can construct these multiple orders here. So coming back to this, so type in RPM, which is going to be our horizontal axis, and so it's speed of 1200. So assume that you're starting at 0 speed, you're starting your machine at 0 speed, and it's going to ramp up to 1200 RPM. So what will that look like? Say it starts at 0, and then assume it ramps up at a speed of 100 RPM every time it ramps up. and it ramps up all the way to 1200, right? So what is its 1x then? Its 1x is simply its 1 times the fundamental speed or the fundamental frequency of the machine. So it's 1 times, and drag that down, and obviously it's going to be equal to the RPM. So now what is its 2 times? Its 2 times is then going to be equal to 2 times the fundamental frequency or the fundamental speed again, and there you go. So its 3 times is now going to be obviously 3 times that. And for the sake of explanation, let's do an 8 times as well and say 8 times the fundamental RPM. And there you go. So now if we were to plot this, real simple, take this, go over to an insert chart, open this up, and there you go. So now let me zoom this up for a second and move this chart to a new chart so we can see it a little better. There you go. So that's your 1 times, your 2 times, your 3 times, and your 8 times, and it should look exactly the same as your interference diagram here. So let me move this to the side for a second so I can show you. And it should look like that. So there's your 1 times, and in this case this interference diagram is showing all the way up to 5000. I just did it up to 1200 RPM, and these are how you construct your multiple orders of run speed. So if your machine was going to start at 0 RPM and ramp up all the way to 1200 RPM, then its 1 times frequency will ramp up at this rate. Its 2 times frequency will ramp up at that rate. Its 3 times frequency will ramp up at that rate, and its 4 times frequency will, or sorry, its 8 times frequency will ramp up at this rate. Now, so what we're doing here with this interference diagram is we're capturing our torsional excitation in the machine, and we are plotting it against the natural frequencies. So let me repeat that on this interference diagram. So what we're trying to do here is we are capturing our torsional excitations at the different orders of run speed, and we are plotting them against the torsional natural frequencies of this machine, right? And so that brings us back to our original concept of resonance. And so if you recall from our first module where we talk about resonance, resonance takes place when your input frequency matches your natural frequency. And so what an interference diagram is, it's a reflection of the input frequencies in the system and the natural frequencies of the system, and where resonances can occur, or at what speeds resonances can occur. If you look at this slide here, you have these input frequencies, which are your multiple orders of input, and you have your natural frequencies, right, these horizontal lines, right, and where your input frequency matches your natural frequency. So when your input frequency matches your torsional natural frequency, then you have resonance. So in this particular case, when your input frequency, in this case the 2 times, matches the first torsional natural frequency, which is at 6000 RPM, which was approximately 100 Hertz, then you have resonance. And so what that means is that the second order, if my machine is running at 3000 RPM, right, give or take, and at 3000 RPM, its torsional excitation at the second order, its second order torsional excitation now matches the resonant frequency or the natural frequency of this machine. And so it creates an interference. So there is an interference point, which is why these are called interference diagrams, which basically means there is a interference between the applied torsional excitation and the natural frequency, the first torsional natural frequency at 3000 RPM. So similarly at 2000 RPM, the 3 times excitation matches the torsional natural frequency at 2000 RPM. So What that means is if your machine was running at 3000 RPM, then your 2 times excitation will be matching the natural frequency of this machine, which means that at 3000 RPM you are at resonance. And if you are at resonance, then it's very likely that you are putting in a lot of energy into the crankshaft and a lot of vibration is taking place in your rotor material, and it's likely that it can fail at this particular speed. So to take this concept a little further, if you were operating at say 3300 RPM, then now your 5 times excitation will intersect or interfere with your second natural frequency, right? Which was, I believe, at around 200 and something hertz. And if you were operating at 4200 RPM, then your 4 times excitation will interfere with your second natural frequency. So what this tells you is, this plot tells you where are your potential issues of concern, or what are your potential speeds of concern in the system. If you were operating at say 2500 RPM, right over here, then in this case your 2 times will be outside of the scope and your 3 times will also be outside because you'll be operating here. So there's no problem here. So at 2500 RPM, you're not close to any interference and you're away from an interference, so you can operate safely here because there's no resonance or there's no potential for resonance here. But if you were operating at 3300 RPM or if you were operating at 4200 RPM, you'd have a problem. But again, if you were operating at say 3700 RPM, then in this case your 4 times your resonance falls in between your 4 times and your 5 times excitation, and so you don't have an issue over here. And that's really the importance of the interference diagram. It tells you where your potential issues are in the system, where your potential resonances can take place, and it tells you what particular order of run speed is your biggest concern, right? And why this is important, again, is because you may have a machine that has 12 orders of excitation, or in this case 10 orders. A 10 order excitation is approximately going to take place at say 1700 RPM, right? Based on this interference. So, and it's going to intersect at the second torsional natural frequency. So, is this a problem or not? Yes, it is a problem because it is at resonance. But there is a catch to this. What if your 10 times excitation to begin with is not a very strong energy? So to begin with, if it's not a strong energy, then even if you're at resonance, then based on a stress analysis, you can say, okay, yeah, I think my shaft will survive, even if I ran at 1700 RPM because of the 10x. But 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 now, if you are still operating at say 1700 or say 1600 to 1700 RPM, now you have a 4 times excitation, also at the same energy. So let me to make this easier to illustrate, I'll just draw a quick line to connect these speeds. So now at 10 times, if your 10x energy is not very high and you're operating at about 1700 RPM, you might be okay. But if you're operating at more like 1500 RPM, then your 4 times excitation, which could be a lot stronger than your 10 times excitation, may be a bigger concern for you. So if you were operator of this machine, you would try and avoid this general RPM range here, because you know that you have a 10 times issue, you also have a 4 times issue, but your 4 times could be greater than your 10 times. But in general, if I were running this machine, I would try and avoid this speed range, because this could be a concerning speed range, because you never know if your 4 times would be a bigger problem or your 10 times would be a bigger problem unless you do a forced response analysis. That's the main importance of an interference diagram. It tells you what corresponding speeds of concern exist in the machine. Basically, if you can read an interference diagram, you have understood torsional analysis. That's the way I see it. Because if somebody presents you an interference diagram of a machine, you can tell right away that, oh, yeah, 2 times 3000 RPM, we could have a big problem because 2 times is a significant energy. If your machine fails at say 1500 RPM, then you can say, yeah, 4 times. 4 times could be a concern. But sometimes your machine may not have failed, but you see high vibration levels at, say, 1700 RPM, and you can look at your interference diagram and say, yeah, we're seeing high vibrations, but no, stresses may be low because the 10 times is not as strong an energy as, say, for example, the 4 times or the 2 times. So, frequency interference diagram is a great snapshot. It's a great snapshot of what the system is all about. It tells you exactly where your resonances are, it tells you exactly what your speeds of concern are, and it gives you an idea of where you can operate safely. And what I mean is what speeds you can operate safely, what windows you have in between where you can park your machine speed without worrying about hitting resonance. So that's the importance of frequency interference diagram. Very important concept. If you get this, you understand torsion analysis. So one other last concept that I'd like to cover on interference diagrams is the differences between an engine interference diagram and a motor interference diagram. With engines, you also have half orders in the excitations, and that's because there's a firing impulse that takes place at half of a revolution of the crankshaft. So what I mean by that is that a full revolution is 360 degrees, but a half revolution is 180 degrees. So at every 180 degrees of revolution, there's a firing impulse that takes place in the cylinder of the engine, and so that's why not only do you see 1, 2, and 3, integer multiples of the orders of torsional excitation, but you also see half orders of torsional excitation. So when you're dealing with an engine, it's even more complicated because not only are you concerned about the single orders or the integer orders, but you're also concerned about the half orders. And some half orders have very significant energy, some half orders do not have significant energy. It all depends on the particular machine and particular engine you're dealing with. But in engines, you have to consider half orders as well. If you're just a motor drive, then in that case, you only consider like a 1x or 2x or 3x. So that's the key difference between an engine interference diagram and a motor interference diagram. So that's all I have for you as far as interference diagrams. And we have an engine model case study, and the interference diagram that is shown here is the interference diagram from diropes. The last thing I want to cover in diropes is how to produce this interference diagram right here that shows the run speed from 3000 RPM to 5000 RPM, right? Because in the earlier interference diagram, I'm showing you the full diagram from 0 to 5000 Hertz. So I want to show you some settings on how to convert that to between a 3000 RPM and a 5000 RPM, and how to plot these half orders in the machine as well. So see you in diropes. So coming back to diropes, I've pulled up this engine model again that we built at the beginning of this lesson. Go ahead and click on post processor. What I want to show you is how to adjust the interference diagram and put it in a speed range that you're more concerned with. So click on interference diagram, and that's the interference diagram. And suppose we're concerned with only the first two modes and we're not so much worried about the last two natural frequencies, then how you can change this setting is you go to settings and you say number of modes, you can change that to 2, and so hit OK, and so now it only plots the first two natural frequencies. And if you want to adjust the speed range over here into a more important speed range of concern for you, then you can click on options, go to settings, and you go to manual speed range. And suppose I want to check, I want to see what my concerning resonances or interferences are between 3000 RPM and 5000 RPM. Then you hit 3000, your X max is 5000, and you hit OK. And so now it changes your scale or your axis to between 3000 and 5000. And the last thing is that since this is an engine, we have half orders which are concerned. So you can go into settings, and then where it says excitation slopes, go ahead and type in 0.5, comma 1, right? And then 1, comma 1.5, 2, comma 2.5, 3, 3.5, 4, 4.5, and 5. And there you go. Now you have your engine half orders in this interference diagram, and you have your integer orders as well in the interference diagram, and you have your speed range of concern. So that's the last thing that I wanted to cover in this lesson. In the next module, I'll get into some more of this detail, and we'll also start moving away from these inertial stiffness models, and we'll get into modeling some actual components like motors and couplings. So see you in the next module. This is the end of module number 2. I hope you enjoyed it. If you have any questions or any concerns, please feel free to reach me anytime. See you soon. Take care.